Before we get into the lesson of today, I'm going to give you a little history lesson. It's 1985, a year that is very special to me because it was the year when I was born. And it was also the year when McDonald's came out with the McDLT. It's the best way to get a cool lettuce in your cheeseburger and also beef that stays with a high temperature. Why would we need this? Because this was going to be avoiding soggy lettuce, which we don't like. That's what we get when we warm up the lettuce, right? So the idea, guys, is that they made a container where you had the part that is hot separated from the part that is cool, and then they gave you your burger like this. So from the kitchen all the way to your house or to where you were going to eat your burger, the burger was gonna stay as hot as possible with the beef and as cool as possible with the lettuce and the tomatoes and all the things that are in the burger that require to be cool. And the idea, guys, this is going to be an example of a thermal insulator that separates the two parts, and it's not gonna let it become in thermal equilibrium. If you put them together, if you put this part of the burger with this part of the burger, they're gonna reach a middle temperature, and that's going to be the thermal equilibrium. That's gonna be what we're gonna be talking about. So to finish this history lesson, this container was there for a while. It has a patent. This is the image of that patent. It has all the indications that would be to specify how to make such a package. As you can see, it's like a regular package, but you have two parts. They're connected, as you can see. You know this thing, but now we have another one, and they're connected. That's pretty much it. There's no other magical components. Pretty much what you know as a burger container. But to continue also with this information, I want to tell you guys that it was very important back then, and they wanted to make it important, so they got this actor to make the advertisement. I don't know if you've ever seen him. He looked like this before, so it was a big deal back then. It was super awesome, and the whole thing was to avoid thermal equilibrium between the parts of our burger so that it would stay delicious with the cool parts and the hot parts. But eventually this wouldn't last too long because, of course, as you can imagine, for one burger you get double the waste. So this isn't very eco-friendly. And eventually McDonald's lost those containers due to those reasons. It's not good, guys. It's not good to make such much waste. Let's think about the planet, guys. Well, okay, let's go to the lesson to understand this better. I'm going to give you this example where you have buckets of water, and each bucket has a different temperature. This one has 0 degrees Celsius and this one has 100 degrees Celsius. The bucket in the middle is empty. There's no water there. And what we're going to do is let's pour some water over here into the empty bucket, and I'm going to do the same thing with the other one. We have some water in there, but the question is, what is the temperature of that water's bucket, of that water, guys? What's gonna be the temperature right there after a while? What do you think that's gonna be? Well, as you could have guessed it, it's going to be right there in the middle. This is pretty easy to guess because both of the buckets are of the same mass, right? So you're pouring the same amount of water, and this one has 100 degrees, this one has 0 degrees. What's between 100 and 0? 50. But what if I would have poured more cold water than the hot water? Well, the final temperature would have been closer to 0. And if I would have placed more hot water than the cold water, the final temperature would be closer to 100 degrees. Let's go back to the lettuce and beef example. We have here a slice of delicious beef coming out from the broil, and this is ready to be eaten, guys. It's ready for a burger. We also have the other ingredient for our burger, which is our lettuce. This beef, this piece of beef has this specific heat, and this lettuce has this specific heat. I don't know if you remember the specific heat of water, which is 4,186, pretty close to this one. The reason that this is pretty close to the specific heat of water, it's that lettuce, it's made up mostly, as most of the other living creatures or living things in the world are made up of mostly water. So that's why things that have a lot of water are going to have a specific heat that is very close to that of water. And this one has a temperature of 10 degrees Celsius. This lettuce, it's pretty cool, came out of the refrigerator. And this beef, it's 50 degrees Celsius. It was a while ago it's been cooked, okay, for a while. 50 degrees Celsius. Could be more if you cook it, but let's imagine that it's now cooled to 50 degrees Celsius. Now, what happens if we put them together? What's going to be the thermal equilibrium of the two things? That's what we are avoiding with the McDLT. How much would we get here? Well, we have this. We're gonna look for the final temperature. That's the symbol or the variable that we're looking for here. We have an initial temperature. As you can see here, it says TI1 and this is TI2. Each one has its own initial temperature, and we have one temperature, a final temperature that is going to be common for both of them. So what happens when you put those things together? Heat is going to be transferred. One of them is going to gain heat, this guy is going to gain heat, and this one is going to lose heat. That's why we have this equation. It says that one of the energies is the same as the other energy but negative. So when you lose energy, it's negative, and when you gain energy, it's positive. That's what this is saying. This is what this equation is saying, that one of them is going to be gaining energy and the other one loses energy. The idea, guys, is that one of these guys is going to be negative. Now, if we have that each substance has its own equation for heat, each one is going to have a Q2 and M2 and so on. And this one is going to have its own equation with Q1, M1, C1, and so on, and so on, and so on, right? Okay, so the idea is that these two things are going to come in contact. That's what we're going to do also with the mathematics. We're going to be equalizing these two equations, but one of them, I got to change the sign to it because it's going to be losing energy, one of them, and the other one gains it. That's why we got to put the negative on one of them. We could also place the negative on the other one. It's going to give us the same result, so don't worry about that. Alrighty, guys. So we have Q1 equals Q2. This is Q1, all of this, and Q2 is all of this. So I'm going to equalize them because when you put them together, the heat that is going to be transferred between the two elements here is going to be exactly the same. And what do we get here? Well, we have here Q2 is the same as over here, but I changed the sign, so I put a negative there because of what I was telling you a while ago. And what we're going to do now is going to be The whole point of this is to clear for TF. I'm just going to show you the mathematics to get the formula to get the final temperature. Alright, that's the whole point of this little section that we're going to have ahead. Okay, so then I'm going to multiply this negative with what's inside this parenthesis. So this negative times the positive becomes negative, and then the negative times the negative becomes positive. We know all the rules of multiplying with signs, guys. So you know what's gonna happen here, right? Okay, I'm gonna continue with this equation on this part. It's right there. What's gonna be next? It's gonna be, I'm gonna multiply this term with this term and this term with this term, so we get this, and that's what we call the distributive property of algebra. But I don't want to go into the details of the algebra because you guys already know this. So we multiply this m2c2 times this and this m2c2 times this one, and we get this term. Alright, that's what happened here. I multiply here and here. That's what we got. And let's not forget what we're looking for, which is going to be to clear for TF. And as you can see here, I have TF on the right side. This TF is on the right side, and we have another TF on the left side. What I'm going to do is this thing, I'm going to pass it to this other side. This is negative, so this is going to become positive. But of course, I don't care about this T1i to be on this side, so I got to pass it to this side. That's why it's over here now. This M2C2 2i is the same as this guy, and this guy over here is right there. Now we have TF and TF on our left side. Now we can do some factorizing. This TFs is going to be, these TFs are going to be staying outside, and what we have inside is going to be M1C1 plus M2C2. This thing is multiplying TF, so what's going to be next? That's multiplying. I want to clear for TF. What do I do next? I gotta divide. That's why we get our formula. This is the formula which we need, which we are going to be using, and all of this is the mathematical process to get this equation, which we will be using for our problem. Alrighty, so going back to the problem, we have this beef with a mass and an initial temperature and with its specific heat, and we have some lettuce over here with some also with its own specific heat, mass, and temperature. Well, we're going to use that equation to get the thermal equilibrium or final temperature when we put those two elements together. What's going to be the final temperature? Well, I'm going to substitute this information into the equation, and since it's kind of a long equation, I'm going to be avoiding the units, and it's going to look like this. Of course, the mass is in grams. You got to change it to kilograms as always. So that's why 200 becomes 0.02 right there. And you see this is M2C2 temperature 2i. It's right there. Temperature 2 is this one. And this is its specific heat, and this is its mass. And over here we have the specific heat of the lettuce, which is 4020. This is the C1, and M1 is the, oh, look, I put it backwards, but it's the same thing, guys. It's going to be exactly the same. As you can see, if you put this over here, it's the same because they're just being added. You just got to be consistent with the M1 with the C1. If you do M1 times C2, that's going to be a problem. But I did not do that error. I have that correct. So I have the C1, I have the mass of the lettuce, I have the specific heat of the lettuce, and also the initial temperature of the lettuce. And on the bottom, I gotta multiply the mass times the specific heat of one of these guys times this times this. There you go. And we have also mass 2 times C2. This is mass 2 times C2. There you go. It's being multiplied. And well, this one is in the correct order, but not this one. But as I told you, it doesn't matter. The reason to this, it's because we have an addition sign in the middle. They're being added, and as you know, when you add numbers in different order, it gives you the same. And well, that's pretty much it. You gotta make this operation, and you get this amount. Okay, but when you do this in the calculator, you gotta be careful not to avoid using the parentheses for the numerators and the denominators, or the numerator and denominator, just one of them of each. Because if you don't do that and you make the division directly like this, if you just do this plus this and then division sign and then this, that's going to be a problem, because the only division that's going to happen is going to be between this term and this term, and not the whole terms on the bottom. That's why you need to put some parentheses. Well, it depends on the calculator. But if it doesn't give you this fraction bar, most likely you will be needing these parentheses. Okay? So, moral of the story, it's that when you put together the beef and the lettuce that have these amount of masses and these initial temperatures, after a while the final temperature is going to be 33.31, somewhere in between 50 and 10. Alrighty, that's going to be the thermal equilibrium that you would get if you didn't use the McDLT. That thing. That's right, guys. Anyways, that's it. So you guys have a great day.